So mathematicians sometimes want to do a little bit of consulting. So for instance, a national park service was interested in the growth of the number of grizzly bears. So they brought a mathematician to see them, and they said 5 years ago there were 10 grizzly bears, and now we have 20, and we're just kind of interested in the future how many we're going to have. And they were willing to pay the mathematician something to come up with some type of model for them. So the mathematician thinking this is going to be pretty easy money, because if we let y be the number of grizzly bears at time t, it makes sense that the rate of growth, dy dt, is going to be directly proportional to the number of grizzly bears. And on video 47, I already learned about this type of growth. It's exponential growth, when the rate of change is directly proportional to how many are there. So I don't even have to solve the differential equation. I've already done it. Or somebody did it for me. And that's what exponential growth leads to if you solve that differential equation. And if I let t equals 0 be 5 years ago, when there were 10 grizzly bears, I know that if I put in 0, I'm going to get y0 to be 10. So I now know that y at time t is going to be 10 e to the k t. And all I really have to do is figure out what k is. Well, I have another piece of information that right now would be at t equals 5, there's 20. So I can just put 20 equals 10 e to the 5 k. I put 5 in for t and 20 in for the number of bears. And if I divide by 10, and then I take the natural log of both sides, I can see that k equals the natural log of 2 divided by 5. And so I've got a model that I can go back and show the National Park Service. They can figure out how many bears they're going to have at any time t. So come back the next day and show them, and we plugged a few numbers into this exponential growth model, and when we plugged in 30, which would be for 25 years from now, we found out that there was approximately 640 bears. And when we plugged in 55, which would be 50 years from now, there was approximately 20,000 grizzly bears. And right away, the ranger told me, no way, this model is no good at all, because we'll never have near that many bears. We have a limited amount of vegetation. We've already done studies to know that the maximum number of bears that our habitat can handle is 100. Well, at this point, the mathematician says, well, you didn't tell me that. You didn't give me all the information. He said it in a nice way, of course, but he said, well, give me another day, because now you've given me new information. It really isn't going to grow exponentially, start here and go up. So the mathematician said, I have to adjust my differential equation. It's not really exponential growth, but it does make sense that the more grizzly bears, the bigger y is, the faster the growth rate. So this still makes sense. But now there's some upper limit of 100. He's saying, boy, if this works, I might want to use it for other models too. So instead of putting 100, he just put L for an upper limit. And said, if I change my differential equation to be this, it's telling me two things. The more bears, the faster the growth rate, and also as y gets close to some upper limit, then the growth rate is going to get close to 0, because this factor will get close to 0. Thinking that then maybe instead of having this exponential growth, that it'll start that way and level out. So maybe we can make our differential equation reflect reality more. Well, just to see what this might look like, he looked at it and said, well, K is positive. We know we have positive growth going on. So K is positive. The number of bears is positive. And L minus Y, if L is the upper limit, is always going to be positive. So I know I'm always going to have this positive growth rate. But I wonder about the concavity. I wonder when that growth rate changes from increasing to decreasing. So he said, I better take the second derivative. And I didn't want to do the product rule. So made it YL minus Y squared. And now, when you took the second derivative, the derivative of YL is just L times dy dt. We're taking the derivative with respect to time. So the derivative of L would, or of Y would be dy dt. And L is just a constant, and the derivative of Y squared with respect to t is 2y times dy dt. And you can factor out a dy dt. And you're left with L minus 2y. So what does that mean about the concavity? Since the growth rate is always positive and K is always positive, this is going to be positive until until Y equals L over 2. So at Y equals L over 2, there's going to be a change from concave up when the second derivative is positive to concave down, which is exactly what we're trying to do. So now we've developed a new growth model where this is Y and this is T, and there's some upper limit, and when Y equals L over 2, so halfway between 0 and L, that growth rate is going to go from concave up to concave down. And he had a model that he thought would make more sense, and he came in the next day to explain this to the park ranger, and the park ranger liked it. Except the park ranger wanted then to plug in the same numbers to see if this looked more realistic. So the mathematician said, well, all I've gotten is this far so far. I wanted to see if this made sense to you. So now we actually, for the next day, the mathematician went back and said, I now have to solve this differential equation for your specific case. So he went dy dt equals ky times 100 minus y, because 100 would be the upper limit. And he knew that he was going to get he didn't know what k was, and he also didn't know what the c was going to be when he went to take the antiderivative. So he knew he needed two pieces of information about y. Well, he had it back here. y of 0 was 10 grizzly bears, and y of 5 was 20. So with those two pieces of information, he figured he can solve this differential equation, but he only knew how to do separable differential equations. So he said, can I separate it? Well, let's see. dy, we have to get all the y's on this side, so we had to divide by 100 minus y, and on the other side is just k, and bringing the dt over there, he was able to separate the differential equation. But now, he had to take the antiderivative of both sides. Well, the side on the right was pretty easy. That's just kt plus c. But this side, he said, what kind of antiderivative can I do? What technique do I know? Well, he noticed that he had a polynomial, a simple one in the numerator, and a polynomial in the denominator that factored. And all of a sudden he started dancing. He said, this is Jackson 5. Or partial fraction decomposition if you want to be boring about it. But anyway, he said, I can separate this into two by going a over y plus b over 100 minus y. And try to get that to be this fraction with just a 1 in the numerator. So he said a times 100 minus y plus by would be the numerator if I put these two back under the same denominator, and I want to set that equal to 1. And then he plugged in y equals 0. That wiped this out and got 100a equals 1. So a equals 1/100th. And then he plugged in y to be 100. And then he got this wiped out, and he got 100b equals 1. So b is also 1/100th. So he could say a 1/100th goes there, and a 1/100th goes there. So he could rewrite this. He could factor out the 1/100th, and then get the integral of 1 dy over y plus dy over 100 minus y. So we had to do two separate integrals, but at least these are very doable. First, to get rid of that 1/100th, he multiplied both sides by 100. So we got 100 kt plus 100 c. Knowing c was just this general constant, he just called it c. And dy over y is exactly the natural log of the absolute value of y. This one is almost in the form of du over u, but the derivative of the bottom is a negative one. So he put a negative here and a negative here. So he got minus the natural log of u, which is 100 minus y. Now, not liking absolute values especially, said, well, the number of bears is never going to be negative. And if 100 is the upper limit, this is never going to be negative. So you could kind of just eliminate the absolute values. Just call them like parentheses or brackets. And then he knew the law of logs, that the natural log of a minus the natural log of b is the natural log of a over b. Okay, I forgot my T in there. So now to solve for y. Said I'm going to e both sides. I'm going to take e to this equals e to this. And e to the natural log, just wipe that out. And e to the a plus b is e to the a times e to the b. And we know that e to the c can just be called c. So we're left with y divided by 100 minus y equals c e to the 100 kt. And now, multiplying both sides by 100 minus y, left with that, but I still have to get all my y's together. So he had to say y equals, and then distribute this through 100c e to the 100 kt minus c y e to the 100 kt. And now he could combine this term over on this side and factor out a y. 1 plus c e to the 100 kt equals 100 c e to the 100 kt. And lastly, y equals, he just has to divide by this, all divided by 1 plus c e to the 100 kt. And he had a model that described what y is going to be at time t. The unfortunate part, he still had a c and a k in it. Well, now is when he's going to have to use these initial conditions. So y of 0 equals 10. So you put 10 for y, and you put 0 in for t. Well, e to the 0 is just 1. So you just get 100 c over 1 plus c. And algebraically, I can solve that. 10 plus 10c equals 100c. 90c equals 10. C equals 1/9. So he could go back over here and in place of c, put in 1/9. But not liking the fractions in there, he multiplied the numerator and the denominator by 9. So we got 100 e to the 100 kt divided by 9 plus e to the 100 kt. And now he had to use the other information, that when you put in 5, y turned out to be 20. So you put in 5 for t, and you get 500k. And this side you get 9 plus e to the 500k. We're almost there, he's thinking. Now I just have to cross multiply to solve, because I want to solve for k. Bringing all the k's together, I get 80 e to the 500k equals 180. And if I divide both sides by 80, I get 9/4 equals e to the 500k. So if I take the natural log of both sides, I can get k by dividing by 500. So now I've got a value of k, and I have an equation that gives the number of bears at any time t. I feel I earned my money this time. That was quite a bit of work. It was a tough differential equation to solve, but I feel pretty good going into the next day. So now I can go in and I stored this in my calculator, and then I put this equation in my calculator, and I was relieved to see that it looked just like this exponential growth rate here. There was 100 right there, and I could see the model looked like that. And when we plugged in some numbers, we first plugged in 30 to see what it was going to look like 25 years from now, and it came out to be 56 grizzly bears. And this seemed like a lot better number that we're looking for. And then, actually, I think it wasn't 30. I think it was 10 years from now. So we plugged in 15. Yes, so 10 years from now we got 56. And the ranger said that makes sense. And then we plugged in 25 to get what it would be from 20 years from now. And it turned out to be 93 grizzly bears. So you can see this makes a lot more sense. The park ranger really liked that, and the mathematician got paid. Now, just to go back really quickly to the model, what would happen, I wonder, if we started with more than the carrying capacity? This number L is sometimes referred to as the carrying capacity. If you started at more than say the park could hold, say you started up here, well, let's do it in red. If you started up here, I wonder what would be different. This still makes sense, but now, since y is always positive and k is always positive, but since y is greater than this carrying capacity, this is going to be negative. So now the growth rate is going to be negative. And if you look at the second derivative, k is positive, the growth rate is negative, and since y is bigger than L, this is going to be negative. So that means the second derivative is always positive. It's always going to be concave up. So you're going to get something that looks like this. And I'm sure you probably don't want me to go through it all, but if you were to solve this whole thing and just changed these, instead of starting out at 10, say starting out with 200 grizzly bears, and then after 5 years, say it went down to 150 grizzly bears, you'd do the same type of work. The only difference, you'd plug in different initial conditions, and sure enough, you'd see that you got a graph that looked like this. So this new growth model, it's not called exponential growth. It's actually given a name, and it's called logistical growth. And in many cases, this is a much more realistic growth model than exponential growth. So, let's just proceed to one more problem. I probably shouldn't share my financial situation, but I'm going to do it this time. The amount of money that I have in savings, which I'm saying M, which is a function of time, is measured in millions of dollars. If t equals 0 is considered to be now, the rate of growth of my money is given by this differential equation right here. And I currently have $2 million in savings. Not bad on a teacher's salary. So, during what time period? Well, I've got 4 different questions here. Now, the first of all, if I'm going to answer this question, I look at this first and see, is that some kind of special growth rate? Well, it's not exponential growth. It's not dy dt equals ky, but it's looking a lot like this logistical growth. Logistical growth is dy dt equals ky times some upper limit minus 1. So the only thing that makes that look different, the k could be there, that could be m, but I don't want 10m, I just want m to be there to make it really look like logistical growth. So what I'm thinking I can do is just divide everything inside the parentheses by 10. And then I get 10 minus m, but to make it the same thing, then I have to multiply the outside by 10. So now I can see that this is exactly logistical growth, so I don't have to go through and solve that differential equation, at least to see the type of growth I'm going to have. If this is the amount of money at time t, and this is t, this is in millions of dollars, and this is in years, I know I start out at 2 million. I know there's 10 as my upper limit, and I know there's going to be a place where it's going to go like that. Now, just to make sure that we did the math right before, let's see what the second derivative would look like here. dm dt is 20m minus 2m squared. So the second derivative is 20 times dm dt minus 4m times dm dt. And knowing that the growth rate is always positive, I can see that this is going to be positive until I get to m equal 5. So I'm kind of convincing myself that that was right that we did before, that the point of inflection, the place where it goes from concave up to concave down, is always halfway between 0 and this upper limit. So, during what time period will savings be decreasing? Now that I've done this, can I answer that question? Yes, it's logistical growth. So you would just say, never, if you could spell right. At the time the rate of growth of savings stops increasing. So I need to know that time. It's not the time that the rate of growth stops being positive. It never stops being positive. But what do we see here? The rate of growth is increasing up to this point, and then it starts decreasing. It's always positive. So what time is that the rate of growth stops increasing? It's at time t, well, we don't know the time, but we know it's when m equals $5 million. But we want to know what's my rate of growth at that point of my savings. Well, that I can get from the differential equation. I can just say dm dt when m equals 5. Notice I don't have to plug t in here. I just have to plug in m. I get 1/5 times 5 times 100 minus 50. Or 50, and what would the units be? They would be the rate of change, so they would be in millions of dollars per year. So at that point right there, there's a really steep growth rate. My growth rate is growing at $50 million per year. Unfortunately, it's not for a long period of time that it's growing that fast. So I've answered A and B. C, when I die at the end of eternity, I figure if I keep doing calculus, probably will never die. So about how much will my savings be? Well, we know it's logistical growth. We've kind of shown that. So we know that always, as m gets close to 10, the growth rate is going to go to 0. So you know the answer to this is, I'm going to have about $10 million. Now, the last part. What will my savings be this many years from now? Well, this is the only one that I can't just do easily. What I really have to do now is I have to solve this differential equation. And I have to put in my initial condition. And you know that t equals 0 is now, and you have $2 million, so you could solve that differential equation. I'm figuring at this point, even though this is designed to work out really nicely, you probably don't want to watch me go through as much as I did in the last one, because it is a little long process, although this one is made to be done without needing your calculator. So I would encourage you to try doing the same thing that I did. In other words, take this and solve that differential equation. Separate the variables. Get dm over m times 10 minus m equal to 2 dt. And then go through the whole process, put in your initial conditions, and you should come out with $8 million. So I'll leave that one to you to try. In general, you're not going to have to do many of these types of problems in your life, but I think it's really good to see how a mathematician takes a real life situation and can use differential equations to describe what's happening in that real life situation, and then solve the differential equation in order to be able to answer questions that want to be answered. So this is something that is done a lot in the real world, and mathematicians earn their living doing things like that. So anyway, I encourage you to try that. Have a good afternoon.